Okay. Good morning, students. Is the connection fine? Can you hear me? Can you see the whiteboard? Everything's clear? Okay. So let's start today's class. So last class we had stopped with redox reactions, right? So there are some problems in redox reactions pertaining to some redox agents. I'll talk about some of those titration questions, right? So we have mainly three of them that you'll come across, right? The potassium permanganate titration, the potassium dichromate titration, and the iodine related titrations, right? So we look at I'll give you the equations. You'll have to remember the redox change that occurs in each of these reagents, which will be essential in solving the question. So you have to remember these few sets of equations, or just remember at least what it converts to. Right? So let's look at the first one, the potassium permanganate titration. Right? So potassium permanganate can act as a reducing agent in acidic medium and in basic medium. Right? So there are three equations for the three different conditions. Right? So acidic condition, neutral to slightly basic condition, and strongly basic condition. Right? So potassium permanganate titration, when you do it, potassium permanganate itself is the indicator, right? So it's a self indicator as well in the titration. For the others, we'll be using an external indicator to detect the change in the endpoint. Right? So let's look at the acidic reaction, right? In the acidic reaction, MnO4 minus, what oxidation state is MnO4 minus? Manganese in permanganate. Give me in the chat, what is the oxidation state of manganese? +7, right? So it's +7. Uh, the manganese in +7 oxidation state, when it acts as an oxidizing agent, it will itself get reduced to Mn2 plus, right, in acidic condition. So when you balance it, I'll just write down, you can do it by yourself. I'll write down the entire equation. So this is in the acidic condition, right? So whenever you get a question, and mostly the question will be in the acidic medium for potassium permanganate titrations, right? So you'll usually be using this equation itself. Now let's look at neutral to slightly basic, right? Slightly basic. Right, so MnO4 minus goes to MnO2. What is the oxidation state of manganese in MnO2? It's +4. It's simple, right? So there is a change of 3 electrons. As you can see, 3 electrons. Previously in acidic, it was 5 electron change, right? So clearly it acts as a better oxidizing agent in the acidic medium. Now let's look at strongly alkaline medium, strongly basic. In strongly basic medium, MnO4 minus acts as a weak oxidizing agent. Right? So it goes to MnO4 2 minus. Right? So it's going from +7 to what? +6. a single electron change is occurring. So if you want to use potassium permanganate as an oxidizing agent, it is best to use it in acidic medium. Right? This is the best condition for potassium permanganate to act as an oxidizing agent. Right? Then we have potassium dichromate. Now, potassium dichromate only acts as an oxidizing agent in acidic medium. Only in acidic medium, it will act as a oxidizing agent, right? So this is not a self indicator. You'll have to add some other indicator, right? Depending on the reaction and whatever indicator functions in that pH range. Right, so we'll only look at one reaction that you have to only be aware of in the dichromate redox reactions. What is the oxidation state of chromium in dichromate? What is it? Give me in the chat. +6. Right, so it's going from +6 to +3 for each chromium atom. Right, so if you look at for 1 mole of potassium dichromate, there is a 6 electron change occurring. Is it clear? So we are only going to be using acidic conditions for potassium dichromate. In basic and neutral, it does not function as an oxidizing agent. So these are the two oxidizing agents that you'll come across mostly. Right? Have you written this down? Can I move on to iodine titration? Okay. Now in iodine titration, you can do it in 2 different ways, right? So we're looking at iodine titrations. One way is if you are titrating with a standard solution of iodine, right? So you're titrating, you're trying to find out the strength of a particular reagent against a standardized solution of iodine, right? So this is known as iodimetry, right? Iodimetry or iodimetric titrations are titrations done against a standard solution of iodine. I presume you know what a standard solution is. It's a solution in which you know exactly what the strength is of that iodine solution, right? We have already calibrated that solution. We know exactly what it is, right? That's what standard solutions are. So iodimetry is against a standard solution of iodine. So iodine, when it acts as an oxidizing agent, it'll itself get reduced to what? The only possibility is iodide, right? So iodine will go to iodide. That's a simple reaction, right? So I'll just give you an example of the reaction that you usually come across. It's against, like you'll try to find the strength of a thiosulfate solution against a standard solution of iodine. So you have iodine reacting with your thiosulfate. Now iodine goes to iodide, right? What does thiosulfate go to? S4O6 2 minus, and this is known as a tetrathionate. This is thiosulfate. Basically a sulfate, SO4 2 minus, with one oxygen replaced by sulfur. So thiosulfate. Is it clear? So what is the oxidation state of sulfur in each of these species. In thiosulfate, what is the oxidation state? So for this, it's not very easy because you'll get, for example, you will, when you calculate using just the formulae, right? Just the formula, if you use the, um, if you use the formula to just determine the oxidation state of each sulfur atom, what will you get? You'll get +2, right? But that's not the actual case, right? You should know the structure of these compounds, right? So for thiosulfate, sulfur is bonded to another sulfur itself. This is the structure of thiosulfate. So the oxidation state of this sulfur is 0, whereas for this, it's +4. So actually, we are only concerned about this +4 change, right? Tetrathionate structure is where there's a bridging disulfide um, bond or species, right? So these have 0, right? And this has +5 each. These two sulfurs have +5. So this sulfur in thiosulfate is undergoing a single electron change when it converts to tetrathionate. Okay, is it clear? Each iodine atom is providing, or it's gaining 1 electron and taking 1 electron from each sulfur of thiosulfate. Is it clear how the reaction is occurring? In this iodimetry, you're using starch as the indicator. This will be the usual reaction that you have to remember for any iodine titration, right? So the difference between iodimetry and the next type is just the sequence in which you do the titration, right? So iodimetry, you're taking, for example, thiosulfate solution and you're titrating against a standard solution of iodine. Whereas in the next case, which is iodometry, right? Iodometry, what you're doing is you are titrating the liberated iodine, right? So you'll do some reaction, right? Some reaction you'll do, and you liberate some iodine in the course of that reaction. So you'll have a, for example, you have some iodide source, right? Let's say you have potassium iodide. The potassium iodide is reacting with some reagent to liberate iodine. That iodine is titrated against some other reagent. Most likely you'll take a standard solution of thiosulfate, right? And you'll do the same titration as in the iodometry, or the same reaction or the equation you'll utilize as you did in iodimetry. So the liberated iodine is titrated now against, in this case, it's a standard solution of thiosulfate or sodium thiosulfate using starch as an indicator. The same reaction. So some reaction will occur previously before this to liberate iodine, right? So let's say use a potassium permanganate, right? You'll use potassium permanganate to oxidize the iodide in the solution, potassium iodide, for example, sorry. Right, so you have MnO4 minus, and you'll have some iodide source, potassium iodide maybe, and you will, when you react it, what happens? The permanganate will oxidize the iodide to iodine, right? And let's say it's in the acidic medium, right? Or whatever, some reaction. It doesn't have to be in acidic medium because it can react in whichever way. So let's say it has reacted, and this is the reaction, the entire equation. We have, I'll just give you the direct complete balanced equation for now. You can balance it by yourself if you want. right? So you have this reaction that occurred, and now you have liberated some iodine. You'll collect the iodine, titrate it against a standard solution of thiosulfate, and you'll do this equation. Is it clear how this two titrations differ? Give me a yes or no. Iodimetry is just titration of some reagent, usually thiosulfate, against a standard solution of iodine. Right? Iodometry is when you have done a reaction with an iodide source, right? Thus liberating some iodine. This iodine is then titrated against a standard solution of sodium thiosulfate. Right? So when you do this titration, you'll find out how much iodine has been liberated, right? Based on how much thiosulfate was utilized from the burette. Then you'll back calculate to understand how much iodide is there in the solution initially and find out the strength of that iodide solution. Is it clear how this entire process works? Titration is done to determine the strength of the unknown solution. Right? In iodimetry, the first type, the unknown solution is thiosulfate. You'll use a standard solution of iodine to determine the strength of the unknown thiosulfate solution. In iodometry, we're trying to determine the unknown concentration or strength of, let's say, potassium iodide or some iodide source. Right? So you'll react the iodide, some specific amount of the iodide or whatever it is, with permanganate. You liberate a certain amount of iodine from that reaction. That certain amount of iodine is then titrated against a standard solution of sodium thiosulfate. From that, we'll know how much or what is the strength of iodine. And then you back calculate for iodide, thus finding the strength of the unknown iodide solution. Right? These are the kinds of problems and equations that you have to utilize for problems related to redox titrations. It won't go beyond this. Right? You have to remember these equations at the very least. Before we move on to the new chapter, states of matter, I'll just ask you if you had any problems with the questions in the modules. Right, so fifth question is simple. I'm sure you must have done that. Sixth question, right? We have just discussed the structures of thiosulfate and tetrathionate. Utilizing that structure, you'll be able to tell what oxidation state the sulfurs have, right? Seventh question, you just have to see whether the other species is undergoing oxidation or not. You have the key with you, right? For all these questions. Do you have the key? Yes or no? Okay, good. Eighth question. Now in eighth question, does anyone have a problem? Have you done this question? Yes or no? Because there is an issue with the way in which the question is framed, right? How many electrons are involved in the following redox reaction? Right, so you have a potassium, you have a dichromate, which is oxidizing the ferrous and the oxalic or oxalate ion, right? So Fe2 plus and C2O4 2- are both getting oxidized respectively to Fe3 plus and CO2, right? So carbon in oxalate has what oxidation state? Each of them have an oxidation state of +3. it's going to a plus 4 in CO2. Similarly, Fe2 plus to Fe3 plus. Chromium is going from plus 7 to plus 3. Right? So when you balance this entire equation, you have two oxidation reactions and one reduction reaction. Right? So when you balance this equation, you will get 6 electrons between the oxidation half reactions and the reduction half reaction. Right? But the answer key said A. Now, this is because the way in which they framed the question is not clear enough. Right? Usually they'll explain or they will tell with respect to a certain number of moles of one of the reactants. Right? They'll say how many electrons are involved for 1 mole of dichromate ion. Right? So then you have a relative scale. Otherwise, when you balance it, you can balance it in multiple ways. You can use fractions, you can use any number of multiplications or divisions to get a different balanced equation. Right? So you have, the question had to be clear as to how many moles of dichromate they are discussing this question with respect to. Right? So for 1 mole of dichromate ion, 6 moles of electrons are involved. Right? Since they only said how many electrons, we'll assume that they're talking about it in terms of molecules. Right? So then we can assume anything. We can assume we are taking 1 molecule of dichromate or 1 molecule of ferrous or 1 molecule of oxalate. It'll all change. Right? You can get any of these answers depending on that. So it has to be clearly mentioned how many moles of dichromate is this reaction pertaining to. Is it clear why the answer key can be wrong for many of you? Yes or no? Or do you want me to solve this? We have done the same balancing previously. Right? For a dichromate, you'll have 6 electron change. For iron, you'll have 1 electron change. For the oxalate, you'll have a 2 electron change. So to balance the oxidation halves and the reduction halves, you have to make sure that the oxidation halves come up to 6 electrons. So you'll multiply both the iron and the oxalate reactions by 2. That will lead us to 6 electron change. So you'll get 6 as the answer, but the answer key said A, 3 electrons. Is it clear what I'm trying to say? It's because the question is not properly framed. Okay. For the worksheet section, 21st question is the same as the previous module question. The rest of it is just oxidation numbers. I'm sure you'll be able to do these. Right? Is it clear? Can I move on to the states of matter? Okay. So we are moving on to module 1, right? States of matter. So in module 1, we'll be discussing states of matter, solid state, and solutions. Now, we'll be discussing in this chapter the different intermolecular force of attraction, which I went through briefly in a previous question while discussing a previous question, right? Then we'll talk about gas laws. So we have intermolecular force of attraction or Van der Waals force of attraction. We'll be discussing gas laws, the ideal gas equation, then the relation between real gases and ideal gases. And the main portion of the chapter, the kinetic theory of gases. Right? This is the most important portion of the chapter. Then we look at liquefaction of gases, that is gas to liquid physical change, the process involved in it. And lastly, we look at some properties of liquids and surface tension, vapor pressure, and viscosity. Right, so the important portion is the kinetic theory of gases and how real gases vary with ideal gas. Right, so let's start with the intermolecular forces of attraction. Now, intermolecular force of attraction can be the primary forces or the, I'm sorry, not primary forces, but it can be ionic forces, which we are not going to be looking at. Right, we are looking at the weak forces, right? Weak forces or van der Waals forces. Right, so mainly the intermolecular force of attraction that we are looking at is the van der Waals forces. Or they are also weak forces or secondary forces. So van der Waals force exists in all molecules. Basically, the form in which it takes is different, right? So we have different kinds of van der Waals forces. The first one we look at, let's look at the intermolecular forces that are exhibited by non-polar molecules, right? Non-polar molecules exhibit London forces. These are exhibited by non-polar molecules. Basically, what happens is a non-polar molecule has no dipole moment, but it has the capacity to get polarized, right? So there, at a particular moment in time, it can instantaneously develop a dipole, right? So the electron cloud shifted to one side instantaneously. So as it's moving about and interacting with different molecules surrounding it, because of the polarization of the other electron clouds and nuclei, it can instantaneously develop a dipole. This instantaneously developed dipole will further polarize a neighboring particle. This type of interaction is known as the London force, right? And we discussed it operates in a range which has a potential energy proportional to 1 by r power 6. Right? It's the weakest type of force, right? Non-polar molecules exhibit the weakest intermolecular force of attraction. Right? Because of this, it has varying properties that we'll discuss later on in the chapter. But remember, it's because of this type of intermolecular force of attraction that non-polar molecules exhibit such properties like vapor pressure, right? Certain aspects of vapor pressure is due to this intermolecular force of attraction. So mainly it depends on the polarizability of a molecule. Polarizability of the molecule, right? Meaning how easily can it get polarized. So a larger size of the atom will ensure higher polarizability. Hence, it will exhibit more London forces, right? So larger atoms. So down the group down the group, you'll see the London forces dominating as its primary intermolecular force of attraction. Then we have the dipole-dipole interaction, which is shown by polar molecules. Right, so dipole-dipole is the same thing as I've drawn for the instantaneous dipole interaction, right? It already has a polarity to the molecule. Hence, it will arrange itself according to the charges and interact with each other, right? So the potential energy varies as 1 by r cube, or inversely proportional to the cube of the distance between them. Dipole is stronger than London forces. You can infer from this. Dipole depends on the dipole moment of molecules. So a larger dipole moment for a molecule will exhibit stronger dipole-dipole interactions. And the special case of dipole-dipole is the hydrogen bond. Right? I'm not going to go into details of this because you already know most of this. Hydrogen bond is a special case of dipole-dipole, so it is also inversely proportional to the cube of the distance between them. Hydrogen bond is stronger than dipole-dipole because it exhibits a higher dipole moment in those molecules. And the last one that we look at is the dipole induced dipole. So this basically occurs in mixtures of substances, right? So you have a dipole or a polar molecule and a non-polar molecule within the mixture, or maybe the molecule itself has a polar portion and a non-polar portion, and how they interact with each other, right? So this also varies inversely to the 6th power of the distance between the molecules. And this depends on both the dipole moment of the polar molecule and the polarizability of the non-polar molecule. These are the 4 different types of van der Waals interactions that you'd observe. Now, van der Waals interaction is present in every molecule, no matter what type of interaction they are primary sources, whether it's covalent, whether it's ionic. Right? So as long as there is some electron cloud and a nucleus, they will interact in a certain manner. Right? So a larger surface area for a molecule means there are more number of van der Waals interaction. Right? So if you see a large surface area for a molecule, it will be able to exhibit more. A large molecular weight indicates that it has a large surface area as well. Hence, it will exhibit a lot of van der Waals interaction. A lot of properties will follow based on this very weak intermolecular force of attraction. Right? The reason is because there will be a large number of them. So it's not that just because a molecule exhibits hydrogen bond, doesn't mean that it's going to have stronger intermolecular force of attraction as compared to a non-polar molecule. Right? What if the non-polar molecule is very large? Right? It's chains, a huge chain of molecule. Right? So it is able to beat the hydrogen bonded molecule by sheer number or the quantity of van der Waals interaction available to it. Is it clear? You have to look at the quantity as well as the quality. Right? If you're comparing similar molecular weight molecules, then you can look at primarily what type of interactions they are involved in. Hydrogen bonding or London forces or dipole-dipole or dipole-induced dipole. But if you compare 2 different or vastly different molecular weights, and if you're comparing vastly different molecular weights, then you have to also consider the sheer number of van der Waals interactions that's available to it. Right? So these are all the intermolecular force of attraction. Now let's look at the gas laws. So the gas laws are a set of laws that determine the way in which gases behave. Right? The behavior of gases is determined by this set of laws. And the laws pertain to the relationship between 4 measurable quantities: pressure, temperature, volume, and the amount of matter which we are taking, right? So the gas laws pertain to the relationship between these four measurable quantities. Now let's look at the four gas laws that determine these relations. The first one is Boyle's law. This is a law pertaining to the PV relation, right? Pressure and volume. Pressure is inversely proportional to the volume, or PV, P into V is a constant. We'll take it as small k, as a constant of proportionality. So basically with these gas laws, the questions pertaining to this will be determined or will be based on the types of graphs that you will be provided, right, by this relation. So P inversely proportional to V, you can write different types of graphs, right? Mainly three different graphs you'll see, right? If you were to just draw a graph of P versus V, pressure versus volume, since it's an inverse relation, you'll see this curve, right? Now, depending on what temperature that you're doing this experiment on, right? So this relation PV equal or P is proportional to 1 by V is at constant temperature and for the same amount of gas at constant temperature and the same amount of gas. For these conditions only, pressure is inversely proportional to V. So for different temperatures, we have different curves. Now, for which, if it was at a higher temperature, let's say T2 is, or let's not go about this way. So at T1, pressure versus volume curve is closer to the origin, let's say, right? And at temperature T2, the PV curve is further away from the origin. Now, how do we determine what is the relation between these two temperatures? This is based on experiments. Later on, we can easily find the relation using the ideal gas equation, right? So the T2 is greater than T1, right? For this condition, you'll see this type of curves, right? So if the temperature is higher, the PV curve will move away from the origin, right? These types of graphs are known as isotherms. Graphs in which the temperature is constant for each curve. Isotherms, right? So this is one type of graph. Then we can have a graph of pressure versus 1 by V. What is the relation then? Pressure versus 1 by V. We'll have a straight line, right? Because if you see the relation, it's directly proportional to 1 by V. Pressure is directly proportional to 1 by V. So you'll have a straight line going through the origin. With the same relation of temperatures, T2 greater than T1. Meaning at a higher temperature, you will see, let's look at the first graph, right? P versus V. For a higher temperature, what do you observe? For the same volume of gas, it will exhibit a higher pressure. That's what it indicates. So these are the two graphs. Then we have a third log graph, right? So if you take the log of pressure and log of volume, what will you get? So we have this PV equal to K relation here, right? PV equal to K. If we take log on both sides, you'll get log P plus log V equal to log K, which is a constant itself. Log P is equal to minus log V plus log K, which indicates the slope of the curve or the slope of the line is negative, and it's a direct relation between the two. So you'll have a graph like this, where if you extrapolate the line towards the log p axis, you'll get log k. Right? So these are the three different types of curves that you'll see. This is Boyle's law. Right? Similarly, you'll see for the other laws, you can make the same type of curves if possible, right? Depending on the relation. Next, we look at Charles' law, which is a law pertaining to the volume and temperature. Volume is proportional to temperature taken in Kelvin. Okay, we are taking temperature in Kelvin, not degrees Celsius. Remember, right? So this is a simple curve, right? So you have V equal to KT. There's no complicated graphs for this because it's a direct relation, right? So the reason why I'm drawing it from a point here is to indicate that this is the absolute zero, right? So this is 0 Kelvin, right? So when temperature is taken to the lowest value, you'll get 0 volume as well, is what you would from this relation what you would get. But that's not actually the case. You'll never get 0 volume because that matter still exists. So it's extrapolated to that point only, right? It does not behave according to Charles' law at low temperatures. Obviously it cannot, because it cannot go to 0 volume, right? Right, so at two different pressures, we have two different curves. So how do we know which is the higher pressure, right? A higher pressure would indicate what? A lower volume, right? So for the same temperature, if you take, a higher pressure should yield a lower volume. So P2 is greater than P1. These types of curves are known as isobars. So this is, keep in mind always, this temperature when you're doing, it has to be in Kelvin. Otherwise, this relationship won't hold strictly, right? There will be some additional term that you have to include. Next, we move on to Gay-Lussac's law. So this is a pressure temperature law. So by this law, they determine that pressure is directly proportional to temperature. Again, Kelvin. Right? At constant, at the same volume and the same amount of gas. That always holds true. Okay. So if we take a pressure temperature graph, it'll be a linear relation with a positive slope. So how do we know what is the relation between these two volumes? At the same temperature, a higher pressure will be related to a lower volume, right? At the same temperature, a higher pressure, or for example, let's same amount of matter. Right. So for the same amount of matter, if we take a constant temperature, meaning the same temperature for both the samples, right? And they're two different volumes, which will give more pressure. Give me the chart. How will you determine if you are given this curve, right? And you are you're given this graph with two lines. one pertaining to a V1 volume and one pertaining to V2 volume. What will be the relation between these two volumes? Which will be higher, which will be lower? How will you determine this? As a side note, these curves are known as isochores, right? Constant volume curves. Right, V2 less than V1 is what Roshan said. What about others? Okay, so we're getting contradictory options. Anyone else? I want to see more answers. Whichever way you analyze, I said constant temperature. Okay, so you can take a different approach to it. So we are taking um, so we're taking the same amount of matter in two different volumes, right? So let's say you have a smaller volume and a larger volume. Right? We are keeping the temperature the same and the amount of matter the same. Right? So we have n comma t, n comma t. These are the same conditions. And now we are looking at whether the higher volume has or right. So if you take this condition, what will you get? You can just go back to your first law, Boyle's law, right? Now we have kept the same amount of matter in two different containers of differing volumes at the same temperature. So the higher pressure, which is pertaining to the V2, would be for the lesser volume. Right? So it should be V1 greater than V2. For this assumption, I'm saying, right? The assumption is the amount of matter is same in both of these conditions. Different volumes are what we are looking at. Right? Is it clear for those of you who have said the opposite? Right. Okay. The fourth law. The fourth law is Avogadro's law, which you're all familiar with. We have looked into this previously as well. It's basically a law pertaining to the volume and the amount of matter, right? Number of moles. So the volume is proportional to n. Right? So there are no graphs pertaining to this. There won't be many questions also associated with this. So now combining all these four laws, they came up with the ideal gas equation. The reason why they said ideal is because they are considering a theoretical gas behaving in this manner. Right? A theoretical gas behaving in this manner will follow all of these four laws. So when you combine them, you get PV equal to or PV proportional to NT based on all those four laws. And including the constant of proportionality, PV equal to nRT, where R is the constant of proportionality, the universal gas constant. Now, depending on what units and what values of pressure, volume, and temperature you take, because N is just the number of moles, right? Depending on the units that you take, you'll get different values of R, right? I'll list down some of the commonly used values and units associated with it. Right, so the most common is 8.314. This is the standard value when you take all of those quantities in their standard or SI units. Joules per Kelvin per mole. So in this situation, you're taking pressure as 1 bar and temperature as 273.15 Kelvin. or you can write this as 8.314 Pascal meter cube. I have just written joules as Pascal meter cube. Then what do we have? Right. So if we were to convert the Pascal to bars and cubic meters to liters, you'll get 0.083, right? Basically 8.314 into 10 to the power minus 2 when you convert Pascal to bar and cubic meter to liter. Now, when you convert the bars to atmospheric pressure, you'll get 0.082, right? It'll be 821, right? There's not much difference. If you want, you can keep that as well. Atmosphere, liter per Kelvin per mole. Is it clear? So at standard temperature and pressure STP conditions, you'll take 8.314 or 0.0831 bar liter. If they have specifically mentioned the pressure is 1 atmosphere, then you will take 0.0821 atmosphere liter per Kelvin per mole. Right. So be careful as to the units you are taking. These are the different ways. Then you can have many other different types. In CGS units, they are not that important. Right. If you want, you can check them out based on their conversion rates. Right. But mostly we'll be using these. Right. So 1 atmosphere is 1.013 bar, which means an atmosphere pressure is slightly higher than a bar pressure. Right? That's why we see this change in the value, the slight variation in the third decimal place. Then some questions you'll come across with pressure represented by millimeter mercury. Right? 760 millimeter mercury is equal to 1 atmosphere. I think this should be sufficient for most problems. Then very rarely you'll come across problems that are utilizing CGS units, right? That is just done. That's not done in JE questions, right? They don't go to that lengths. They mostly operate within these units that I've mentioned here. Right. So now looking at this expression PV equal to nRT, we can get different relations, right? So we can write number of moles as mass or weight by molecular weight, right? PV equal to nRT, you can write as mass by molecular weight, which I'm representing by capital M for now. So you'll get this relation. Now mass by volume is density. This is one expression you can utilize in solving some questions. Right? This density, right, is clearly not the density that you're usually thinking of. This density is the vapor density because we are talking about ideal gas equation. So this is the vapor density of a molecule, of a gas. Right? So how do we define the vapor density? Right? The vapor density is defined as, I'll take a new page. The vapor density is defined as the mass of a gas. Vapor density is defined as the ratio of the mass of a gas to the mass of hydrogen gas at the same conditions of pressure, temperature, right? Pressure, temperature, volume. Keeping all those constant, the ratio of the mass of a gas to the mass of hydrogen is the vapor density. Now, if we take it to the molar scale, you can replace it by the molecular weight of the gas by molecular weight of hydrogen, which is 2. Right? So you'll get vapor density is equal to molecular weight by 2. And this is another formula that you can utilize, or they will expect you to use in certain questions, right? The next topic is about partial pressures, right? So there's a law pertaining to the partial pressures of gases. Dalton's law of partial pressures. Basically, if you have a mixture of, let's say you have a container and you have a mixture of gases, right? I indicate the different gases as fully shaded, unshaded, and for let's say stripe. Okay. There are these types of molecules in this container, this closed vessel. Right? So this exhibits a pressure. Let's call it P total. What Dalton's law states is that the total pressure exerted by a mixture of gases is equal to the partial pressures exhibited by each individual gas, right? So what he's suggesting is that it's a additive summation of the different pressures associated with each of their molecules. Basically what it means is, if we take the same container, right, and we divide each of these molecules into a container of the same size, and you experimentally verify the pressures associated with each of them. If you sum them up, you'll get the total pressure. So the first container that you see has a mixture of gases. The second container only has the solid shaded gas particle in the same volume container, right? So whatever volume this has, same volume here, right? So whatever temperature we're keeping that same as well in all of these vessels. They are identical vessels kept at same temperature. So what the Dalton's law says is that the total pressure is the summation of the individual contributions from the gases. Right? So we can get to a relation or utilize different methods to solve these type of questions by looking at just the number of moles involved. Right? So this we can write as N total RT by V. Right? So if we look at the ratio of, one partial pressure to the total pressure, we can write this in terms of the moles as well. N1 RT by V by N total RT by V. We'll get N1 by N total, which is N1 plus N2 plus N3. This is essentially mole fraction of that particular gas molecule. So the partial pressure is a factor, or is the mole fraction times the total pressure. P1 is the mole fraction into the total pressure. Something like a fraction of, or what is the contribution of the gas to the total pressure is related to its mole fraction. Is it clear? So we can use the same principle in questions pertaining to, let's say they're giving a they're giving a scenario in which you have a particular gas molecule suspended over water. Right, so you collect, there are many experiments, right? The downward displacement of a gas, upward displacement. There are many experiments. So in those experiments, you utilize water as a way to collect gaseous molecules or gaseous products, right? So when you collect them over water, water itself has a vapor pressure associated with it. Some molecules of water exist as water vapor in that sealing, right? So when you measure the vapor pressure of the gas after collecting it, it is not purely due to that gas. There is a contribution by the water vapor as well, right? So you can utilize the Dalton's law to solve those questions as well. So you have the total pressure, which is equal to the partial pressure of the dry gas plus the aqueous tension, right? This is known as the aqueous tension, which is the vapor pressure associated with water vapor, right? So aqueous tension is usually the saturated water vapor's pressure. So whatever pressure that you're experimentally measuring, right, when you displace it through water, right, you have displaced the gas through water and you're measuring the pressure exerted by that container, it is not just due to that dry gas. It is also a factor contributed by the water vapor. Is it clear? So this will be the experimentally observed value that you will be provided. And they'll ask you what is the vapor pressure of dry gas. You'll have to subtract the aqueous tension, which has certain values at certain temperatures, right? That is experimentally already tabulated, right? They will provide you with the aqueous tension at that particular temperature in which they have done the experiment. So you'll just subtract it from the total pressure and you'll get the vapor pressure of the dry gas. Is this clear? Yes or no? Okay. Now let's look at a different concept that you may be tested on is diffusion, right? When you talk about diffusion or effusion, right, this can be determined by Grant's law of diffusion. This is also applicable to effusion. Now, what is the difference between the two processes? Right? Diffusion is the process in which a gas will occupy a space without any external force applied to it. Right? There is no, it is just by virtue of its nature that it will spread and occupy the space of the container. That is diffusion. Whereas effusion is when you have a small hole, you have a container, let's say. You have a container in which your gas is there and you poke a hole through it, right? A poke a hole at one point, at one surface of the container. Now, the way in which the gaseous molecules exit this hole, that process is known as effusion. Right? Is it clear the difference? Diffusion is when you open the container completely and how these gas molecules will spread. Whereas effusion is through a small hole. But the laws in related to diffusion and effusion follow the same mechanic. At least at this level, that's enough. Right? So basically what they're trying to ask you in these types of questions are related to the rate in which this diffusion occurs or the effusion occurs, right? So if you're given the same temperature and pressure, how do the rates of rates of diffusion of two different gases compare? It's usually a comparative question, right? So under the same temperature and pressure conditions, the rates or the rate of diffusion of a gas is inversely proportional to the square root of density of that gas or vapor density of that gas. Right, so the rate of diffusion, R represents the rate of diffusion is inversely proportional to the vapor density of the gas. So when you compare two different gaseous molecules, you'll compare their two different rates, and the ratio of the rates will be equal to the square root of d2 by d1. Now, from the previous explanation on vapor density, we know that vapor density is equal to the molecular weight by 2 of whatever gas. So you can also write this relation in terms of the two gases involved. So you'll get square root of m2 by m1, where these m's are the molecular weights of the molecules of the gases, right? You can also look at the diffusion rate as the amount of gas, right? The volume of gas diffusing over a certain time, right? So you measure the amount of gas that is diffusing over a period of time, and the ratio of those two will give us the rate of diffusion. So you can also write it as V by T, where V is the volume of gas diffusing or effusing. Is it clear? So now you can relate this with this formula, and in whichever manner they ask you the question, you'll be able to solve it. Right? Sometimes if in relation to some of those factors, they'll ask you the question. Right? Is this clear? Okay. Behave, and how does this theory's assumptions lead us to some results pertaining to their kinetic energy, the way in which temperature will affect the movement of the molecules, things of that nature, right? So when they developed the kinetic theory of gases, they came up with some postulates or assumption, right? Some of the assumptions that are inherent in this theory. You need to understand these assumptions and postulates to further understand what the merits of this theory are and what are the demerits. Right? Where does it fail? Where does it succeed? So the first assumption that they took was that the molecules are treated as point particles. Are treated as point particles, meaning they are occupying negligible volume. Right? You can say that they have very small volumes that are negligible. It's not zero volume, but it's close to zero, right? Volume tending to zero, right? So that is the first assumption, that they are point particles or point masses. The second assumption is that there are no intermolecular forces of attraction. No intermolecular forces of attraction between the particles. I'll come to some of the conclusions that you can infer from these assumptions after I go through the entire set. And what are the failures due to each of these points also I'll come to. Now these particles are in a constant random motion. Right? This is one of the assumptions, that these particles are in a constant random motion, meaning they're always moving about. Right? And there is no predetermined route for it. They're random. When they move in straight lines. They move in straight lines and collide in perfectly elastic collision. So they move in straight lines, but when they collide with each other, they collide in a perfectly elastic manner. So that means what? That the energy and momentum are conserved. So after collision, they'll again move in a straight line and collide with another molecule. Then, right. So when they move in different, when they're moving in different motions, they all have different speeds, right? The particles have different speeds. associated with them, and hence different kinetic energy. So on an average, if you are, for example, you kept a sample of gas molecules in a box, right? From outside, when you observe it, obviously, the gas molecules don't have a net motion in any direction. Otherwise, you'll notice the box moving, but they don't have that. So the average speed, right, comes out to 0. I'm talking about if you're containing it in this container, right? But if you're observing uh, within the within a portion of the molecules, they obviously have a net direction somewhere, right? Even though they are moving randomly, right? But if you take the net of the entire gas in a particular vessel, obviously they're not moving anywhere, right? So they are random motions which cancel out everything else. So when we talk about speeds and kinetic energy in this theory, we are always talking about averages, right? We are not talking about a single molecule's speed and kinetic energy, at least while analyzing the bigger properties, right? So these are all the different postulates or assumptions inherent in the kinetic theory of gases. Now let's look at each of those points and see what it implies, right? So point particles means what? They clearly have negligible volume, right? So if they have negligible volume, you can explain the compressibility of the gases, why gases are highly compressible, right? This can be explained um, from this assumption, right? But it is also excluding the fact that the molecules have or are occupying a considerable volume in the vessel, right? So that is one of the demerits of one of the bigger demerits of the theory. What about the second point? No intermolecular force of attraction. No intermolecular force of attraction means what? They are not going to come close to each other, meaning they are not going to, they'll come close to each other only due to the randomness of their motion, not because there is something else pulling themselves to each other. Right? So this can explain why gases will diffuse and occupy all the space available in the room or the container, right? Because there's nothing pulling them together or pulling them back. So they can radiate outward. Right? So you can explain how they occupy all space due to the absence of intermolecular force of attraction. Constant random motion, there's not much inference you can get. A lot of things can be related to the random motion. Then what else? Yeah. So the fourth point, moves in straight lines and collides in perfectly elastic manner. This can explain how they exert pressure on the container because they're colliding against the walls of the container. That is what's leading to the pressure that you observe. Right. So these are the main points that are part of the kinetic theory of gas. Now let's look at what what the different speeds and different kinetic energies actually mean. So they're all moving in random motion. Right? So let's say there are n number of molecules and they're all moving with their own individual speeds in different directions. So let's say you have 3 particles and they're all moving in different directions. Now their individual, let's say individual velocities are u1, u2, u3. We only talk about the average for a sample of gases, right? So if you look at the average speed, it will be obviously u1, u2, u3, so on till un divided by the number of particles n. Okay. Now there is derivations based on this. right, to get to the kinetic energy um, final term. Right? I'm not going to go through the derivation. Right? I'll give you the expressions. If you want, uh, you can check up some textbook, or if you want to know, you can ask me separately. It's not very necessary because they're not looking at the derivation is simple, and so there won't be questions based on uh, some of the various assumptions we do in the derivation. It's a simple derivation, so the result itself can be utilized in solving questions. Right now, based on the way in which these particles behave as a whole, right, we can have a certain amount of statistical data on it. Right, these particles behave according to the Maxwell-Boltzmann statistics. What you usually come across is that particles or uh, uh, concepts or numbers are following a Gaussian distribution, right? Right. This is not Gaussian statistics. This is particularly following Maxwell-Boltzmann statistics. It's slightly different. We don't have to go into the formula of what Maxwell-Boltzmann's probability distribution is, right? So the particles' velocities follow Maxwell-Boltzmann statistics. We look at the probability distribution of the particles versus their speeds, right? So we are plotting the fraction of molecules with speed u, right? So this is the fraction of molecules, and we're plotting it against the speeds, right? So u. So a point in this, or a data point in this graph suggests that a certain fraction of molecules, right? Let's say the fraction comes out to say half. Okay, let's say this is pertaining to half. Half the molecules will have a speed of u1. Right? Did you understand what this curve actually represents? It's fraction of molecules, right? Half of the molecules have speed u1 is what that data point suggests. Right? So I'm going to erase that. That's just to give you an idea of what this uh, graph represents. So Maxwell-Boltzmann's distribution function is not like the bell curve that you observe in Gaussian distribution, right? So this curve tends to zero at infinity. So the curve behaves in this manner. If you can see, it reaches the high point quickly and then it decreases very slowly to zero. So what does this graph suggest? That this particular fraction, this apex point represents, has this particular speed here, down here. So we don't know what the fraction is. Okay, this is just a qualitative graph. This is not an exact graph that I'm providing. Right, so maybe let's say it's half or 0.5. Okay, just for understanding the statistics better. This suggests that half the molecules have a speed u1, right? And that is the highest fraction of molecules. Right? Any other speed has a fraction of molecules associated with it less than this. That's what this means. So this would be the most probable speed or velocity, right? The most probable velocity or speed. Most probable because the most number of particles are associated with that speed, right? So this is the most probable most probable velocity or speed, however you are discussing it. Now we have two different other speed terms that we are interested in. Right? We have the average speed, which is, as you have calculated, just the normal average. The most probable is based on just the probability distribution function. So when you calculate or when we did experiments on this, we found out that the average speed is higher than the most probable speed. The average speed is higher than the most probable speed, but it is associated with a lower fraction of molecules. Okay? The third one is known as the RMS speed, or the root mean square speed, URMS. This is average speed. This is the RMS speed, or the root mean square speed. The RMS speed is higher than both of the most probable and the average speeds, but it's associated with a lower fraction of molecules. Right? Is this clear? How the terminologies and all the terms are associated with each other? Now, based on calculations, they found out the formula for each of these speeds. Right? So the most probable speed is equal to the square root of 2r. Yeah, let's go with RT. Or yeah. I'll come back to this a little while. Okay, don't get confused now. Just focus on the number root 2. Right? Square root of 2 kbt by m. Right? I'll come to what kb means in a while. The average speed is square root of 8 by pi kbt by m. And the RMS speed is equal to square root of 3 kbt by m. As you can see, square root of 2 is lesser than square root of 8 by pi, which will come out to be a little more than 2. Right? And then square root of 3 is obviously higher. So we have these. You have to remember these quantities to calculate certain other. Right? So these three formula are important. Now getting back to the Boltzmann statistics, what this curve suggests is that particular molecule, let's say it's nitrogen, right? That nitrogen gas molecules at a particular temperature behaves in this manner with these speeds. All the molecules in that closed container at temperature T behave in this manner. Now, what will happen if we change the temperature? If we change the temperature, what happens to the molecules? They get excited, right? You're providing more energy to the system, hence their kinetic energy will increase. If their kinetic energy increases, their velocities or their speeds will increase, leading to a higher average speed in the container. So when you increase the temperature, how will it change the curve? If initially the curve was this way, so we're not changing the number of particles, right? We're only changing the temperature. So let's say this is associated with T1. When you increase the temperature, the speeds will increase. So obviously have to go to the right. But when it goes to the right, let me change the color. Right, so it'll go to the right, but the fraction of molecules associated with each of those speeds will decrease as well. So there's a flattening of the curve in a sense. Right, is this clear? So this is T2 and T2 is greater than T1. Is it clear? Yes or no? I'm looking at the chat. Okay. So this was for the same molecule, let's say. Let's say we were taking nitrogen. Now what happens if you were to compare two different types of molecules? Let's say you're comparing nitrogen and chlorine, right? Clearly chlorine is a larger molecule, right? So what will happen to that? A larger molecule means that it will move slower, right? If it moves slower, for example, let's say this is our nitrogen curve, and we're taking the same number of um, molecules in nitrogen and chlorine. So chlorine will have a smaller, let's do this. Yeah, it'll have a smaller speeds associated with it. Its most probable speed, average speed, um, and its RMS speed will be lower than nitrogen. Because it's much more massive, it has lower speeds. But we're taking the same number of particles in both cases, so the areas under the curve, under their respective curves, will be equal. My graph doesn't seem to look equal, but they're supposed to be equal. Is it clear? Okay, so this is how some of the questions you can have comparisons for the Boltzmann statistics, right? Maxwell-Boltzmann statistics. Now let's look at some of the results that you get from the derivation of kinetic energy of gases, right? So kinetic energy, or the average kinetic energy, is proportional to the temperature. So if you increase the temperature, the kinetic energy of the molecules will increase, right? So you'll finally, after the derivation, you'll get some of these results, right? So the average kinetic energy, right? Right. I'll change this. Let's say the kinetic energy of 1 mole, right? So I'll just indicate it by the subscript mole, right? So per mole of the gas, the kinetic energy is related to 3 by 2 RT. This is for moles. This is going to be a little, okay. So remember, this is per mole of the substance. Per molecule, it is 3 by 2 kBt, where kb is the Boltzmann constant. And kb is equal to R by Avogadro's number. Is it clear? So make sure you use the right expression. If you're talking about a mole of the substance, right? You'll use the expression 3 by 2 RT to indicate the kinetic energy of 1 mole. If you're talking about a single molecule, the kinetic energy associated with a single molecule is 3 by 2 kBt. Right? And kb and R are related in this manner. Kb is equal to R by Na. This is clear? Make sure you don't make this mistake here between these two expressions. Therefore, two different things, a molecule and a mole. So when you compare certain quantities, you have to use the correct expression. So this is basically it for kinetic theory of gases. Right? These are the major points I've hit upon. If you want to know the derivation of it, you can ask me later on, right? If you have, it's not that important, so you don't have to waste your time on it. Now let's look at how an ideal gas compares to a real gas. Now, ideal gas is a concept that we have taken up so that we can start off our discussion of uh, gaseous behavior, right? So, and we got some results associated with it. Now, the reason why real gases don't behave like ideal gases is because of the manner in which we have started our discussion of gases in the kinetic theory of gases. So the first two assumptions, point masses and the absence of intermolecular force of attraction. These 2 points make it difficult to or make it difficult to analyze real gases, because real gases do occupy a certain volume, whereas uh, ideal gases don't, and that's fine, right? And the second point, intermolecular force of attraction. There is intermolecular force of attraction, so the uh, pressure exerted will be different from the ideal gas equation, right? So now let's look at some of the evidence associated with it, right? So we have certain graphs of real gases comparing them to the ideal gas equation. So there's this one graph, PV versus P, right? PV versus P for an ideal gas. Wait, let me use a different color for the ideal gas. Let's say the ideal gas is the blue line. This way you'll be able to better compare the two. And the compounds given, so I'm taking this directly from the NCERT textbook. The compounds associated with each of these curves, you have to remember how they behave to a certain extent, right? Because some of the questions are asked based on these graphs that I'm providing now. Right. Is it clearly visible what each of them represent? This line is helium. This straight line is hydrogen. This one is CO2. And the last one is methane. Now you can see that hydrogen and helium more or less at least behaves in the same functional manner, right? The same, they are straight lines with a positive slope, but they're still straight lines. Whereas in the case of carbon dioxide and methane, they have a lot of deviation from it. Their behavior changes drastically as you increase the pressure, right? So if we look at the way in which their volumes behave with change in pressure, right? So for example, if we take the PV graph of the ideal gas, let's say it behaves this way. The real gas will, so the red line is the real gas, blue line is the ideal gas. Meaning when you are when you're increasing pressure, right? When you're increasing pressure means you're going up this way. So when you're increasing pressure and you compare at a higher pressure, the real gas occupies a larger volume than the ideal gas. V real is greater than V ideal at a high pressure, right? At high pressures, we observe this. Whereas at low pressures, what do you see? You'll see the opposite slightly. They're coming really close together there. So the change is quite minuscule actually, right? So at high pressure, we can say that the real gas volume is greater than that of the ideal gas. Right? It's because of those two assumptions. First of all, the real gases have a significant volume occupied by the particles. Secondly, there are intermolecular force of attraction, which will reduce the pressure exerted by the molecules on the container because they're pulling them inward slightly, right? We're not assuming that they are colliding freely against the walls of the container. So to understand this difference in their nature, they came up with the compressibility factor, Z, which is equal to PV by nRT. Basically, they are checking how different is the PV left-hand side of the equation versus the right-hand side of the equation, right? So if Z comes out to be equal to 1, if Z is 1, it is ideal gas behavior, right? If Z is greater than 1, what does that mean? Z greater than 1 means PV is greater than nRT, right? Z greater than 1 means PV greater than nRT, or you can say for the same pressure, as you can see from this PV graph here that I've shown with the real versus ideal, for the same pressure, the volume is greater than that of the ideal case. So you can say PV is greater than 1. Let's say you're taking at the same temperature for the same number of molecules, right? So Z greater than 1 means PV is greater than 1, which implies at the same pressure that you are keeping these molecules, the molecules exhibit or exist in a larger volume, right? So the molecules are less compressible, you can say. So when you're trying to, less compressible. When you're trying to compress them, you have to apply more pressure to reach the same compressibility as the ideal gas. So they are less compressible. They are pushing outward more, right? So this will also be associated as the molar volume being greater than 22.7 liters at STP. Now, what about Z less than 1? Just the opposite. Just the opposite. It will be more compressible. Or the molar volume is less than 22.7 liters. What conclusions can you make from this? So Z greater than 1 implies a positive deviation from the curve. A Z less than 1 means a negative deviation from the ideal gas curve. So if you look at the PV versus P graph, right, you can see that hydrogen and helium show positive deviations throughout the pressure range. At low pressures, carbon dioxide and methane show negative deviation. So when is this possible? When is a molecule more compressible or less compressible? Let's look at positive deviation. Less compressible means what? There is more repulsive forces acting, right? There is more repulsive forces acting between the molecules. They're pushing each other away. That's why we are observing a larger volume that these molecules are existing in. Whereas in negative deviations case, it's more compressible, meaning, let me just finish this, Aditya, then I'll get to your question. Negative deviation means it's more compressible, meaning what? The molecules are attracting each other further, so they're coming closer together. They're coming closer together, meaning the attractive forces are greater than the repulsive forces. Whereas the positive deviation is repulsive forces are greater than the attractive forces between the molecules. Right? Okay, Aditya. If we are given a particular real gas, then how can we predict the graph? They will not ask you they will not ask you in that manner, right? They will give you some, there will be some means through which you can get to a conclusion on its general behavior, right? You can't, they won't ask you like, let's say sulfur dioxide, how does the graph vary? They're not going to ask you that. That's why I said many of their questions are based on the molecules in the graph they have given in the textbook, right? So CO2, CH4, hydrogen, helium, they can ask you direct questions on how they behave. And you should know because these are the molecules presented in the graphs they have given, right? Did you understand how you can analyze this positive deviation and negative deviation? Okay. Now, based on this, we can draw another graph that they have provided where they're plotting the compressibility factor with pressure. So Z equal to 1 for all pressures. I'll draw by the blue line. We have hydrogen. It's not wavy actually, it's because my hand is shaking a little while drawing. Okay, let me just finish just two more curves and I'll go to the previous page. All right, let me just go to the previous page. Ajwin wants to draw that. Z is equal to PV by RT, right? So Z greater than 1 means that PV is greater than RT. So I'm keeping the temperature constant so that I can, otherwise there will be too many factors and we won't be able to understand what exactly is happening. So usually analysis of gases are at the same temperature and we are looking at the pressure volume changes, right? That is what we are more interested in. As far as your syllabus is concerned, that is the most important way in which you analyze gases, right? So I'm keeping temperature constant and I'm taking the same amount of gas. So how does that vary, right? So PV is greater than RT and RT, sure, but then there's that one thing, right? So I just want to look at how it's increasing or decreasing as compared to previous. So what I'm comparing is whether it's increasing or decreasing in some effect. Right? This is just for analysis sake. Right? So if we were comparing two different ones with the number of moles and temperature the same, P1 V1 will be greater than P2 V2. Did you understand, Aditya? One is more compressible, one is less compressible. That's what it basically suggests. You can think of it that way, but actually what we are doing is, let me write it. Ajwin, did you finish writing that? Can I go to this page? Yes or no? Ajwin, did you want to see this more? Okay, I'm going to assume you finished. Okay, so what I'm doing is I'm comparing the real gas to the ideal gas. So when Z is greater than 1, what does that mean? Right? What is the conclusion we got? Right? It's less compressible. Right? But how do you get to that from Z? We don't understand really what Z means, right? We're trying to understand what compressibility factor actually indicates. So we can say PV by nRT is greater than 1. What does that mean? PV is greater than nRT. Okay, so let's say this is the real gas pressure and volume, and we're taking the temperature and number of moles the same. In this case, V ideal is equal to nRT. Right. So if we're keeping these two same, we can essentially say P real V real is greater than P ideal V ideal. And now I'm comparing the two situations. Is it more compressible? Is it less compressible? So at the same pressure, what happened? V real is greater than V ideal, meaning it's less compressible. Is it clear now, Aditya? It's a comparison. So you have to assume we are keeping that ideal gas at the corner to look at how the real gas behaves with respect to that ideal gas. Clear? Okay. So this is another graph for compressibility factor versus pressure. Oh, okay. One second. Ajwin wants to complete writing this. He got disconnected for a moment. Okay. Right. So this is indicating how each gases behave with respect to an ideal gas. So you can see that hydrogen has a positive deviation throughout. Nitrogen behaves like an ideal gas at low pressures and then has a positive deviation as you increase the pressure. Oxygen has a negative deviation over a lower range of pressure. As you can see, it's below the ideal gas blue line. And then at a point, it starts showing positive deviation, right? So what does that indicate? A negative deviation at a lower range versus positive deviation at a higher range. So at a lower range, it is showing more compressibility, meaning the attractive forces are larger than the repulsive forces. But after a point, when the molecules are too close together, the repulsive forces are increasing. Hence, they start showing positive deviation. Right? So most molecules will show first a negative deviation, then a positive deviation. Nitrogen has a very small range in which it's showing a slight negative deviation, but it's almost negligible, I guess. We don't know the scale of this graph, right? So hydrogen shows positive deviation alone. Same for helium, right? So just understand the nature in which they behave. Now, another aspect of this is related to its temperature. How does temperature change the behavior of a real gas with respect to ideal gas? So if we look at Z versus P for different temperature ranges of a particular gas, right? So we have our ideal gas line here, Z equal to 1, Z equal to 1. As we increase the temperature, what happens, right? Let's say you're taking something like CO2, right? So for CO2, let's say it's like this. Right, something like that. So we have T4, T3, T2, T1, right? So as you increase the temperature, you'll see that the real gas starts behaving like an ideal gas over a small range of pressure. As you can see, the curve is flattening at the negative deviation section. Slowly it's flattening. So as it flattens, what it means, it's starting to behave like an ideal gas. So as you increase the temperature, T1 is the largest temperature, T4 is the lowest temperature. As you increase the temperature, the range of or the real gas will start behaving like an ideal gas over a small range of pressure. This range only, not the entirety, right? So that temperature is known as the Boyle's temperature. Boyle's temperature or Boyle point, or Boyle's point, right? So the temperature at which a real gas behaves like an ideal gas over over a wide range of pressure is known as the Boyle's temperature. Is it clear? So above this temperature, about T1, you will start seeing only positive deviation is what they are suggesting. Below this, you will see a first negative deviation and then a positive deviation. Is it clear? Okay, so this is with respect to the real gas, ideal gas relation, how they graphically represent it. Now let's see what happens to the ideal gas equation now that we have understood the way in which it changes, right? Obviously now the volume occupied by the gas is lesser than, okay, so let me rephrase this. This equation that we see is the ideal gas equation. So this pressure that we are writing here, this term P, is the ideal gas pressure, but when you're doing experiments, what is this P actually? It's the pressure that we are experimentally observing, right? But when you are using a real gas, right? When you're using a real gas, what you get, the pressure that you see, right? The pressure that you see is actually lesser than that of the ideal, right? The P observed is going to be lesser than the ideal pressure because there is intermolecular force of attraction, right? Similarly for the volume that the molecules can travel around or occupy, in a sense, be effective, let's say. It's not the correct way, but I'm just trying to differentiate the two. The effective volume in which these gases can travel about is lesser than the ideal, right? Meaning the volume of the container now is actually lesser than that of the ideal gas container. So how do we substitute for Pi and Vi in the ideal gas equation, right? Clearly, let's look at the volume first, right? The volume that the container effectively has is going to be the total volume of the container minus the volume occupied by the particles. That is the effective volume of the container now. That we can fit into the ideal gas equation. What about the pressure term? The pressure term, or the pressure that we observe through experiments, is going to be lesser, right, than the ideal pressure. So to fit it into the ideal gas pressure value, we are going to have to add a corrective term. That corrective term is an square by v square. Right? B corresponds to the volume of a particle. So this entire thing is the excluded volume. NB represents the excluded volume. They are not point masses and they do have intermolecular force of attraction. So this entire term, when you correct for the observed pressure, will indicate the ideal pressure. Meaning, if it were an ideal gas, this is how much pressure it would exert. Is it clear what the correction actually means? Okay. So now at different conditions, we can apply different approximations, right? At high pressure, what happens? At high pressure, meaning you're applying a lot of pressure to that container. You can essentially disregard, right? At high pressures, the P observed value is a very high value, right? So essentially P observed will be much larger than this corrective term. So we can just write it as P into V minus NB equal to nRT. And when you rearrange this, you'll get PV by nRT is equal to 1 plus NB by nRT BP by RT, right? So what does it mean? This is Z. Z is equal to 1 plus something, meaning Z is greater than 1. Z is greater than 1 means this is positive deviation. So at high pressures, we will get Z greater than 1, positive deviation. As we have seen in the graphs previously, at high pressure, we saw positive deviation for almost all molecules. Now at low pressure, what happens? At low pressures means there is not much, everything is spread more far away, right? The volume is much larger. So the volume term is much larger than the excluded volume. This becomes negligible now. It's okay to assume them to be point masses, right? So we will have P plus AN square by V square into V equal to nRT. Finally, if you simplify this, you'll get Z equal to 1 minus AN by RTV, or Z is less than 1, which is the negative deviation. So many of the molecules at low pressures show negative deviation, and that is correct according to the graph as well. Is this clear? Okay, so this is, as long as it's clear to you what the expression means and how it changes, you'll be able to solve any question with respect to this, right? Now we have just 2 more topics left in this chapter: liquefaction of gases and some properties for liquid state, right? Liquefaction of gases, it's easy, but the graph is a little bit confusing if you look at it. So I'll go through it. I know there isn't much time, but I think there should be sufficient time to understand this. As long as you understand how to read the graph, it's fine, right? So I'll draw the graph and explain accordingly, right? So let's look at liquefaction of gases, or the process of gases converting to liquids, right? So you're drawing a PV graph, right? Pressure versus volume. Now we know that a normal PV graph of a gas is in this manner for a particular temperature, right? Right, let's say T1. Now, as you reduce the temperature, what is going to happen? As you reduce the temperature, this graph is going to go down towards the origin. It's moving. We have already seen this, right? We are reducing the temperature. At a particular point, as you're reducing the temperature, you'll see a certain change happening, right? Previously, what did you see? As you reduce the temperature at a particular temperature, as you increase the pressure, right? So now we're looking at one curve. As you increase the pressure for a particular temperature, the volume is decreasing as per Boyle's law, right? at this particular temperature, when you are doing the same experiment, you're increasing the pressure, you see a volume decrease. But at a certain point, you'll notice that at a constant pressure, you're seeing a volume decrease as well. And you can see there's a flattening here, right? Beyond this, you'll suddenly notice that the substance has turned into liquid, and the compressibility now is much lesser. As you can see, it became more steep, right? So this is the point in which the change of gas to liquid occurred. Right here, it all exists as gas only. Right above this, it exists as gas. But when you reach this particular temperature, which is known as the critical temperature, you can see the formation of liquid. So critical temperature is the temperature above which gases will not liquefy, No matter what you do, above this temperature, gases will remain as gas alone. It will not be able to liquefy, right? Now, if we go to a lower temperature, what happens? What happens is, yeah, okay, fine. You'll see that the range through which the liquefaction occurs increases, and you'll see the steep slope. So it's a liquid here, it's a gas here. Right? Now, if you lower the temperature more, the range at which the liquefaction occurs also increases. So the temperature is decreasing as you go down. Temperature decreases as you go down. The pressure associated with this critical temperature is known as the critical pressure, and the volume associated with this critical temperature is the critical volume. Is it clear? Now, the graph they have given in your textbook is that of CO2. For that, the critical temperature is approximately 31 degrees Celsius. If we were to think of CO2 as the graph. Did you understand how to read this? For a particular temperature, as you increase the pressure, the volume will decrease according to Boyle's law. As you reach critical temperature, you'll see there's a drastic change in the state of matter at a particular point, which is the point of liquefaction. As you increase the pressure, suddenly it compressed very quickly, and then the compressibility starts decreasing. It's a steeper slope on the liquid section. Then if you lower the temperature more, the range through which the liquefaction occurs is larger. In this region, this dotted line region that I have put, CO2 exists as a gas and a liquid phase. It's a continuous phase of gaseous CO2 and liquid CO2 in this region here. It's a continuous phase. Right? Did everyone understand this? Next class, we look into the liquid properties. That's just 3 or 4 of them. And then we'll move on to solid state. Is that fine? All right. Thank you.